Hello, everybody. This presentation is for the third workshop on parallel AI and systems on the edge. Thank you for joining our talk. I'm Aravind Sankaran, a second-year PhD student in high-performance computing from RWTH Aachen University, Germany. My supervisor is Professor Paolo Biantonisi, who's a director at the Supercomputing Center at Umeå University, Sweden. So the title of our paper is Performance Comparison for Scientific Computations on the Edge via Relative Performance. So by scientific computations, we mean a code that consists of a sequence of mathematical tasks. We do not make any hard assumption on what these tasks could be, but in general, each task evaluates some mathematical expression. For instance, it could be a linear algebra expression consisting of a chain of matrix-matrix multiplication, or it could be an evaluation of a least square problem in a loop. So these tasks are commonly seen in neural network-based applications. So for our discussion here, we only consider a scientific code with this abstract representation, because whatever application then you can think of, we can then fit it to this abstract representation. So typically, when such scientific codes are run on an edge computing environment, there could be many instances where various mechanical components have to interact with one another, and hence this scientific code has to be split among various devices and accelerators. And finding the optimal split is important, very important, especially for latency critical applications such as autonomous driving, where every millisecond matters and you can't afford to make a mistake. So in this example here, every car has to independently solve a computer vision problem to infer its surroundings, which is generally complex. But let's say which is complex for a single car, but when 5 cars are traveling in the vicinity, this computer vision problem, which is a scientific code, can be split efficiently among the nearby cars. By doing this, not only that each car now has to solve a simpler problem, thereby saving a lot of energy, but also all the cars can join force and act as one supercomputer to solve a more complex problem and make a better visual representation of its surrounding. And this will eventually make autonomous driving more safe. The problem here is, of course, the network strength between different devices is not going to be consistent. So the optimal split of computation changes over time, and the split of computation has to be determined more dynamically. So in this work, we aim to move towards that goal. Another application is digital twins, where one creates a digital replica of a real system. So digital twins have diverse applications, but since we spoke about autonomous driving, in this context, a car can create a digital map of another car. And if this can be done, you have a richer representation of a surrounding, right? Although a single vehicle may not be able to solve such simulations fast enough for practical applications, when many vehicles can coordinate, this can become possible. So all these applications here can be represented as a scientific code with a sequence of mathematical tasks. And we have to choose the right split. And depending on how you split the code, the performance are going to be different. So to begin with, we first have to capture the performance variation for different splits. So let me start with a simple illustration here. Consider this code where there are two mathematical tasks, two loops, L1 and L2, evaluating some matrix expression. So for now, we assume that L1 and L2 cannot be executed concurrently. That is, these loops can run either on a CPU or a GPU. It could be any device, but for now, we assume it's CPU, GPU, and CPU is an edge device and GPU is an accelerator. And there are 4 possible implementations. Either the whole code L1 and L2 are run on a GPU or a CPU, or either one of the loops are offloaded to the accelerator GPU. Another thing here, the time taken for data transfer between devices are included within the loops L1 and L2. So eventually each of these split are going to differ in terms of performance, and that's what we want to show now. So the distribution on the right that you see here are repeated measurements of execution time for these 4 implementations. When the whole code is run on the device or a CPU, the execution times are a bit higher, but when you offload it to an accelerator, you see an improvement, which is the red distribution. However, when you offload just a part of the code to the accelerator, that's only the second loop, you see a little bit of performance gain, that is this green distribution. So these differences in performance are mainly due to differences in data movements. Although theoretically it is possible to reason out the difference in performance by counting the floating point operations or simply counting the data movements, but in many modern applications, the devices always have some energy optimizations happening in the background, or have some background processes running simultaneously. Hence, it's really not straightforward to analytically quantify these performance. So, but the takeaway message is eventually each split is going to have different performance profiles and we want to capture it. So what exactly can we infer from these performance distributions? Of course, we want to select one algorithm here, but for now, we do not want to select just the best, but first create a ranking. Why do we need a ranking? Because when we later use here, we are running the experiments and getting these distributions. But when we use neural networks to select the algorithm without having to run them, these neural networks learn by differentiating good from the bad. So we should also know how bad each algorithm is from the best, right? So we need a ranking of these distributions first before selecting it. But there's a problem with ranking. We see some implementations can have overlapping performance. For instance, yellow and blue here. So these two implementations seem to be performance equivalent. That is, we cannot say one is better than the other. Therefore, we really do not want a hard ranking of the candidates, but to do a clustering, we cluster them into performance classes. So by looking at this figure, we could say green could be in cluster 1, red could be in cluster 2, and the last two algorithms could be in cluster 3. But even with this clustering, when you examine closer, red and green are partially overlapping. Shouldn't they be in the same cluster? Moreover, when this sample of measurements becomes low, it would get more and more difficult to see how much of these distributions are overlapping. So what exactly should be the point of separation between these two clusters is really not clear in practice. Therefore, what we thought would make more sense is a soft clustering, where a candidate can be assigned to more than one cluster. So we are aiming for something like this. That is, the distribution red here belongs to cluster 1 with confidence 0.3 and cluster 2 with confidence 0.7. So every algorithm is going to have these soft scores. I'll tell you how we get this table in the coming slides, but for now, let's just remember that we are aiming for a soft clustering where a candidate implementation can belong to more than one performance class. Before going on to how we can actually get this table, let me discuss what we can actually do with such a clustering. So here's another example with 3 loops, and there are 8 different implementations. First of all, with this table, we can find out if using another vehicle or another accelerator helps at all. So here, running all the 3 mathematical tasks on the edge device, that is algorithm DDD, results in the second best performance class. But offloading the all the 3 tasks to an accelerator, algorithm AAA, pushes it down to the 4th performance class. That is, it's becoming worse. But offloading just the last part of the code, the task 2 and 3 to the accelerator, gets it to the best performance class. Right, okay, but do we have to select this rank 1 code where a part of the code has been offloaded? Well, in the autonomous driving example, I really don't want to offload my computations to another car just for meager gains, right? I want to do it only if it's absolutely necessary. So in that setting, the best algorithm is not always based on execution time, but also based on additional criteria. And these additional criteria can be applied over this clustering table. Another instance of example is uh, when the devices are heating up because of thermal throttling, you may want to switch a part of the computation to another device, and then after some time, switch it back to the edge device. And with this table, it's possible to know which part of the code should be offloaded so that we do not lose so much in performance. And with this, we can also come up with fault tolerant policies. For instance, if one of the devices break down, then how should we split the computations without losing much of performance? And finally, one of the most important application is, okay, recall this scientific code is a sequence of mathematical tasks. And if this number of tasks is increasing, it's not practical to measure all possible combinations and get the distributions and then get this table. So in such an instance, we would need a performance model that would automatically do this clustering. And what this table here can be obtained for just a sample of the measurements in the search space, not the whole search space, but just on a sample. And this can be used in conjunction with reinforcement learning to automatically extrapolate this table to the entire search space. So here, this table can be used as a ground truth to train performance models. But the discussion of performance model is not within the scope of this talk today. So what we are going to discuss is, given a set of possible splits, how can we capture the performance differences via soft clustering? So now we will explain how we can get this table by running the experiments. So let algorithm 1 through P be different ways of splitting the scientific code. And in order to cluster these algorithms into performance class, the execution time of each algorithm is first measured n times. We do not assume that the measurements are made under a stable environment. That is, to ensure that the measurements are invariant to system noise, we do not execute n measurements of an algorithm consecutively, but kind of shuffle them. That is, let's say we have 3 algorithms and we have to run each of them 10 times each. We create a concatenated list of execution instances and we shuffle the list and then measure them. So the execution of algorithm are not consecutive, but shuffled among each other. And after having all the measurements, we have a histogram for each algorithm. And we compare these histogram pairwise and then sort them. And then we merge ranks. So what do I mean by merging ranks? For that, let me talk a little bit about comparing two algorithms. So the result of comparing two distributions can either be that one is better than the other, one is worse than the other, or the two algorithms are equivalent. So we are aiming for a three-way comparison here. Why three-way? Because in practice, we do not have access to the true distribution of execution time. But what we have is just a snapshot of this true distribution. And only if there is enough evidence from this snapshot that one algorithm is better or worse than the other, we go for it. Otherwise, we simply say the two algorithms are just equivalent. So let's, how do we do this? We do not just use a single statistic from the distribution, but do multiple comparisons. So let's say we are comparing two algorithms, R and G, and we have 30 measurements of each. We sample 5 measurements from each algorithm, R and G, and compare their statistics, let's say minimum. And we replace these 5 samples and sample 5 measurements again, and then compare their minimums. And we repeat such comparisons many, many times. And only if the algorithms are consistently better or worse than the other, we say that the algorithms are dominating. Otherwise, we just say there is no enough evidence. And when there's no enough evidence, the algorithms are equivalent. And we control this consistency by setting the threshold parameter. Higher threshold simply means stricter condition for comparison. That is, even if there is a slight overlap of the distributions, the algorithms will be evaluated as being equivalent. One problem here is that quite often, especially when the number of measurements of each algorithm is very low, the comparisons would not be consistent. That is consistent. If let's say if R is just exactly at the threshold of being greater than B. So it depends on the threshold parameter here. So if it's just at the threshold, then repeating the bootstrapping strategy would not give consistent result, because in some cases, the result of the comparison can alternate between R equivalent to G and R better than G. So there is an element of non-determinism here. And in the coming slides, I'll show you how I deal with this. So for now, we use this three-way comparison function to sort the algorithms. We use a bubble sort procedure with a modification that we merge the ranks of two algorithms if they are performance equivalent. So we use this procedure. So let me illustrate these with the example that we discussed in the beginning, 4 ways of splitting the two loops between CPU and GPU. Initially, we do not know which is the best, so we do not know the order. So we first randomly initialize them with consecutive rank and do the bubble sort. So this relies on 2 main rules here. We swap the position of the algorithm if an algorithm occurring later in the sequence is better than the one occurring earlier. So here AA occurring later in the sequence is better than DD, so we swap ranks. The next rule is if the two algorithms are equivalent, we merge their ranks. So here in the second comparison, you see DD equivalent to DA, so we merge their rank. So both have rank 2 now. And we repeat these rules for each step. Another thing you have to notice here is that these comparisons are not transitive. That is, in step 3, if DD is equivalent to DA and AD is better than DA, does not necessarily imply AD is better than DD. But still, since we know in this step that AD is better than DA, we swap the positions, but we do not update the rank. We still keep the same rank. So now you see 3 algorithms are having the same rank too. But what's special here is, although they have the same rank, there's also an inherent ordering within this cluster. So there are 3 algorithms in cluster 2, and the order of algorithm in this cluster is important. So this is not just a set. And this is going to solve most of our problem. So in the final cluster, AD is getting rank 1, AA is rank 2, and DD and DA are rank 3. So this is agreeing with the histogram we have. But recall that if the comparisons are not consistent, especially when n is low, the ranks may also not be consistent. For example, in the last step, instead of AD better than AA, if AD was just equivalent to AA, then both AA and AD would share rank 1 and other two would have rank 2. And then there would be just 2 clusters. And more, if AD was at the threshold of being better than AA, then the result of comparison would alternate between AD better than AA and AD equivalent to AA, and the final rank would be different. So we repeat the sorting procedure k times on the same set of n measurements. In doing so, if AD is equivalent to AA 30% of the times, then AA would obtain rank 1 with confidence 0.3 and rank 2 with confidence 0.7. And this number is what we call a relative score. And we do this for all the algorithms. Thus, we do a soft clustering where every algorithm can be assigned to more than one cluster, and they all have a corresponding confidence or relative score. And another thing, if you notice in this table, the light blue, DA, and the red distribution, AA, they are distinctly apart in the graph, but this table indicates a chance of being in the same class. This is kind of counterintuitive, right? But recall that there is an inherent ordering within each cluster, that although DA and AA they are in the same cluster, DA can never come above AA. The scores will always be less for DA than for AA. So the information is anyway captured, and it's not a problem for our methodology. So the order within each cluster is important. And this table, as we mentioned in the beginning, can be used as a starting point to derive a variety of applications, such as charting reliability policies, training performance models, etc. So to summarize, we consider a scientific code that can have different ways to implement them, and we describe a methodology to cluster the alternatives into performance classes. The main reason for doing this clustering is because this table creates a discrimination among the alternatives. The information about discrimination is very important to train neural network-based approaches, because neural networks learn by discarding the bad from the good. So our methodology will form a basis or act as a ground truth to train neural network-based approaches, and this will be the continuation of our work. But why do we need neural networks? Let's recall the autonomous driving example, where there were 5 cars traveling close to each other, and we have a scientific code. We know how to split the different ways of splitting them. Here in that example, the network speed between different vehicles is not constant, and the number of devices are also going to keep changing. But in the performance cluster we discussed in this talk, the number of devices were fixed, and the network strength between devices were pretty consistent. And if we follow the measurement-based strategy for the autonomous cars example, where the network strengths are changing, it's not possible to measure all possible scenarios, all possible network strengths by this measurement strategy. So what we can do is use a neural network to learn the sensitivity of our cluster table to the changes in the network speed, and then extrapolate the table without running the experiment. So this is just one application we quote as an example, but overall the takeaway is this methodology can be used as a basis for many other applications. So thank you. We are grateful for financial support from Deutsche Forschungsgemeinschaft for this research, and we'd be glad to take up questions and comments. Thank you.